Okay, so very good evening to everyone. Welcome to the last lecture of the qualifier camp of STEMS 2021. Finishing the proceedings is a renowned mathematician who needs no introduction, Professor Ravi Vakil from Stanford University. Professor Vakil, one of the most prominent algebraic geometers in the world, obtained his BSc and MSc from the University of Toronto and his PhD from the Harvard University under the supervision of Dr. Joe Harris. His research interests include enumerative geometry, topology, and of course, algebraic geometry. He is currently a professor of mathematics and the Robert K. Packard Fellow at Stanford University. Professor Vakil's prominence in math was established right from a very young age when he had won 2 gold and 1 silver medals in the prestigious International Mathematical Olympiads, in which he represented Canada. One of the gold medals was with a perfect score in 1987. He is not a once or a twice, but a 4-time Putnam Fellow, which is considered to be one of the hardest and most prestigious math contests. A very few of his numerous accolades include the Alfred Solon Research Fellowship, the American Mathematical Society Centennial Fellowship, the National Science Foundation's Career Fellowship, the Presidential Early Career Awards for Scientists and Engineers, which is the highest honor bestowed by the US government for outstanding research, and many more. Today, Professor Vakil will amaze us with his curiously titled talk, From Doodling to Mathematics, an article that goes by the same name for which he won the Chauvenet Prize in 2014, which is awarded for outstanding expository articles on any mathematical topic. In this talk, he'll take us through how observations play a key role, and pondering over it will help realize deeper connections between objects. Without any further ado, over to you, Professor Ravi Vakil.
Great, thank you. Thank you very much. Let me know, is my sound all right? You can hear me fine, it sounds like?
Yes, perfect.
Wonderful, great. So thank you very much for the chance to be here. It's a real honor to be asked to speak to you since you represent a good chunk of what the future mathematics will look like over the next while as well. So what I'd like to tell you about, oh, first I should say thank you also for having your videos on, because I feel like the pleasure for me of speaking to many people in India is getting a chance to actually see parts of India as well, even if they're at home in the dark. So what I'd like to tell you about is something that I've been thinking about for really almost all my life, when I was maybe 5 years old, and it's something which the way I think about it is that it's going to look like play, and it's going to look like there's nothing, that it's just all in fun, which is certainly true. But in my mind, this is what mathematics is really about. It's finding patterns in nature, explaining them and extending them. And much of what mathematics is really about is asking the right questions, not just questions. And that's what I want to do. And this is what science, I think, is also about when you actually do science. So I'm going to try to find interesting questions buried in just the kind of doodles we do every day. So, and the things I'm going to try to tell you about lead to and connect to lots of deep mathematics in many fields, including mostly fields in which I'm not an expert and don't know too much about, although possibly more than you. But the entire point of being a scientist or a mathematician really is, it's important to not just stay in your comfort zone and to be comfortable thinking about things outside of what you really know much about. So I'm hoping you feel open to asking questions and thinking about things and not just treating me like an expert who's telling you some sort of delivered wisdom. And I definitely want to get to things such as Hilbert problems, current cutting edge research, work of a number of Fields medalists and things like this. So I'll ask a lot of questions, and I will give only some answers. And the first question I'm going to ask is a very basic one. So the kind of doodling I did when I was small and ever since is something which looks like, let me increase the size, where you're sitting somewhere, maybe watching a math lecture, and you have a pen and paper, and you just start around some shape, you just start trying to draw as close to it as you can without sort of touching. When you iterate, you do this around the previous two. And so here's an example of it on your screen.
Excuse me. So at the moment, the slide doesn't seem to be changing. So
that is,
yeah.
Okay, let's see if I can. Does it look like it is? Are things changing now?
No.
Okay, so in that case, I've had this happen sometimes before. And sometimes it takes me a minute to have, okay, now let's see. Do you see something or no?
No, it's still just the title slide.
Okay, so then I'm going to stop sharing and restart. Thanks for letting me know. Share screen, cable. How about now?
1 second, it's 1 second. It's still saying it. You've started screen sharing.
Okay, that means that hopefully it's coming. I guess one of the joys of Zoom is that we can talk to each other across thousands of kilometers, and the downside is that there are technological problems. Has it turned up yet, or not yet?
Not yet.
Not yet.
Could you try restarting their screen sharing again?
Great. Let me stop share. Share screen. Great. Once again, it says you are screen sharing, but I'm not sure what
it's still waiting. Yeah, we can see it now.
Good. Okay. Let me know if there's a delay let me know if there's too much of a delay in what I'm writing. Okay. Let me try to write something now. I'm scribbling.
Yeah, it's almost immediate.
Oh, excellent. Wonderful. Good. Okay. So now you can see the kind of doodle, hopefully more successfully, of where you kind of just draw around something like this. And what I'd like to do is just use this one doodle and ask questions about it and see what happens. But maybe the first thing I'd like to do is find out how many people have doodle like this themselves. So if you've doodle like this, now this is my first poll. Just you say yes if you are someone who has done things like this, and that this is, I'm not just making this up. And I don't know how best do you want to do a poll or thumbs up? I'll let the hosts figure out what best to do.
A thumbs up for this?
Yeah, thumbs up sounds good. Put your thumbs up if this is something you've done. And this means I have to quickly zoom through some screens to see. And if you are looking through, you'll see lots and lots of thumbs up. I guess I don't know, is there a thumbs down? Then thumbs down if you do not do this, if this is strange.
There are plenty
of thumbs downs. Okay. So the point I want to what I want to say is that at least the thumbs up you can see people, this really is somehow in nature. I'm not just making this up. I guess if your thumbs are down, then I think you should see yourself as a strange person when you look at like all the people with thumbs up. Those are the normal people. And if you've never done this, then I'm sorry for you. But okay, in any case, many of you will at least accept this is something that you might do and ask questions of. And so let me ask questions. And let me start with the question that I noticed when I first started doodling this, which is the first I remember, I might have been perhaps 5 years old. And one thing you notice is when you start doing this, you start off with something maybe with sharp edges.
Sir, you have muted yourself.
Good.
Yeah.
Good.
Yeah. Okay.
Good. So when I was small, looks like you can hear me. When I was small, one of the first things you notice when you do this is it's aesthetically pleasing. Why is it aesthetically pleasing? There are lots of different reasons, but one thing you notice, or I noticed, that was getting rounder and rounder. So the way I would think about it is that the doodles were getting more and more like circles. And so what does that mean? Well, when you're 5 years old, or you don't worry about questions like that. You just notice it and maybe wonder why. And so as we try to answer it, we have a question to ask first, which is what are we doing? How do we formalize the question. And now let me formalize something. And before I formalize it, I just want to emphasize that turning it into mathematical notation seems like you lose some of the, it makes me feel bad because you've turned it into something seemingly ugly. But I want to emphasize that there's no content in mathematical notation, in this mathematical notation. It's just a language with an embedded logic. So that's the only reason, but it's a very important reason that we do this. So let me make it formal. So if I have a shape X, I want to call the rth neighborhood of X to be all those points. So the rth neighborhood is going to be all those points that are close to a point of X, to some point of X. So all I've done in this, I know if you're comfortable with set notation, you're already happy, but I just want to reiterate that there's no additional content. It just lets us be precise. And then once we've said this, that we have all the points with the distance r of our set, the question is, if we start with some shape like this X, then we doodle around it and again, and so forth. And that's the ... Does it become more and more circular? Okay. So actually, even before I, maybe before I even go into the question, I would point out that this 5-year-old idea of repeating something, ... means limit, of course. So when you're very small, you do understand the notion of limit. The formalization is complicated, but the notion of a limit is not. It's a very fundamental idea. Great. So but inside, as soon as you make a definition, you realize there's a new notion that you might not have paid attention to, which is this R, which is how big a doodle do you do? And as an example, I may do a doodle around X, and let's say my doodle is size 2. But you're more coordinated than me, and so you are able to do a doodle of size 1. And I could, so does the answer depend on this? Well, somehow it shouldn't, you could believe. But if I want to make that more precise, really obviously, your doodle is contained in my doodle, because everything that's within 1 point of something in my shape is certainly within 2 points. So that's a dumb, well, that's not dumb, but it's not that exciting. But let me ask you something trickier, which is if you doodle twice around yours, you're kind of getting a total of 2 units away. And if I doodle, so my question is, if you doodle twice, 2 doodles of size 1, how does that compare to my doing a single doodle of size 2? So now I would like to take a vote of whether you think, and this will have to be a poll, I think. Before you, I think the hosts know how I want this set up, but before I ask it, my question is going to be, are your doodles at least as big? Or is my doodles, are they at least as big? So when you look at this question, maybe it's not so clear. And now as you think, I'm hoping you're subconsciously beginning to have an opinion. I want to try to make clear why you really should have an opinion. And I don't care if your opinion is right. And it's the same because you have to wonder about something and then have some expectation. And there's nothing wrong with thinking something might be true so long as you're willing to change your mind when presented with evidence. And it's a reason why when you do scientific experiments, the scientific method involves usually having a hypothesis. I think this will happen, or I wonder if this will happen. Let me find out. You don't just mix chemicals in a test tube and say, oh, let's just see what happens. Maybe something will blow up, who knows? So it's important for you to have a guess just because it's honing your intuition. Part of doing science or mathematics is to learn how to think correctly. So now I'm ready to take the poll. I'd like to ask, maybe people have questions before the poll, but if not, the first poll would be, do you think your double doodle, N1 of N1 of X, is at least as big as mine, which is N2 of X? And I'm ready to, all I want, essentially I want a poll with rough numbers. It doesn't have to be exactly precise on how many people think this.
Okay, so I'm launching the poll right now and you have like about 30 seconds.
Excellent. And while you are voting on that, I'll then ask, really at the yes, so don't bother voting no, it doesn't matter too much. I just want, so more the numbers. So it should be almost 100% yes if no one's voting no. But okay, around 52, 58, 59.
About 10 seconds left.
One awkward thing is I don't want people to be voting based on other people's votes. So really, this should be your own. I'm very unimpressed if you are just repeating someone else's opinion. If you're a sheep.
I think it's majorly stabilized. So
Right.
83%, that is 85 participants say yes and 17% say no.
Okay, and how many people think, just to make it simple, have a new poll, how many people think the N2 of X is at least as big, the my bad doodle? I guess it's
So
fairly
I'll start
clear.
that polling now. I'm starting about the second poll now, which is
We
about,
have about 30
N2 of
seconds.
X.
We'll have some time for this. And,
Yeah, so 30 seconds more for this again.
and the question is going to be, as you'll see, I'll just talk so to have you, while you're doing this, which is how many people, I guess it's clear it's going to be about 17, I guess. We'll think yes, because 17 said no the last one, maybe. But how many people think the single red doodle of size 2 is going to be at least as big? And again, I guess I don't know if people have questions in between as well while we're waiting.
Okay, this is a mix. 60%, about 55 participants say yes, and 40%, about 40 say no.
Great. Okay, good. So now we have some interesting mathematics. We have the pigeonhole principle, which says that given the number of participants and the number of yeses and nos, someone must have voted yes and no, must have voted yes 2 times. So let me just ask, if you're willing to admit this in public, how many people, you can just do thumbs up for this, voted yes both times? Okay, don't be shy. Okay, maybe be embarrassed, but not too shy. Okay, so I can already see people are lying because there are too few people admitting to their bad behavior. Okay, good. So at this point, I want to say that those of you who admitted to bad behavior, assuming you're telling the truth, you were right twice. You were right. But the answer to both questions was yes. The questions were, of course, not exactly opposites. And if you voted yes to either one of those questions, right, you should pat yourself on the back. If you voted yourself twice, you can pat yourself on the back twice. And if you did not vote, then you're wrong. You had no chance of being right. So you are. So that's the biggest possible mistake. That's worse than voting no. Okay, great. So in fact, they're the same. And you should think about this. Another reason why you want to vote is when you draw this, as I just did with red and green, they look kind of close to each other. Some of you might have, no one asked, but someone might have wanted to ask what I meant by at least as big. Like, that's kind of a vague statement. How can you vote if you don't know exactly what that means? But we can actually try to check by being very precise, writing a computer program, using string. This is where now even theoretical mathematics is fundamentally an empirical science, because the way in which you discover what's true is not by just free associating, but by actually trying to do things. And if you wrote a computer program and were very careful and try to be more and more careful, you discover the amazing empirical fact that the red and green are exactly the same. So for some reason, at that point, you would guess, conjecture, hypothesize, or if you're a physicist, you just say it's true. It's great because I can make jokes about physicists here, and no one can stop me because you're all muted. So that in fact, they are the same shape. So they are exactly the same, and that cannot be a coincidence. There has to be a reason. And then maybe with a little bit of mathematical taste and experience, you'll say, aha, if that's true, then the right statement should really be that if you do a doodle of size B and then a doodle of size A, it should be the same thing as doing a doodle of size A plus B. So 1 + 1 = 2 is really what is a special case of what should really be going on. And so let's figure out why this is going to happen. And so the reason why it works, once we think it through, turns out to lead you to the following notion. And remember, the question you're asking is when you're 5 years old, and it's going to go through the following thing, which you know when you're not much older than 5, which is one of the most important facts in mathematics, fundamental facts in mathematics, which is the triangle inequality. And which says that if you're trying to get from point A to point C, then going in a straight line is the best way to go. or put differently, if you're going to go through a point B on the way there, then you're definitely going to take at least as long, or it's going to be at least along a route, unless B happens to be on the road between A and C. And because when you draw it this way, it looks like a triangle. That's why it's called the triangle inequality. But this fact is something, again, you instinctively know when you are very small. So we're led to this fact by asking this question. And so now let me use this to show, let me shrink this, that n of A of n of B of X is n of A plus B of X. And how do we show this? Well, we essentially just take the vote we had before. If the people who said that the first side was at least as big were right, and the people who said the second side was at least as big was right, that means that they're exactly the same. So let's just do this. So if you take a doodle of size B and follow it by doodle of size A, and I want to compare that to a doodle of size A plus B, well, then if I can take a step to something, and I can take a step of size at most A plus B, I can get there in 2 steps of size at most A and at most B by just cutting my step in a ratio of A to B. So this means that anything I can get to in 1 big step, I can get to in 2 smaller steps. Well, how about the other direction? Well, if I can take a step of size B, followed by a step of size at most A, how do I know that step I can get to in a single step of size at most A plus B? That's the triangle inequality. So to say it really precisely, the statement we're trying to prove is true exactly because the triangle inequality is true. And to say something in a fancier way, if you want to do this on on any other kind of shape, not just the plane, it's still going to be true. You could do it in 3-dimensional space. You can do it on the surface of a sphere. Anything where the triangle inequality is true, this is going to be true. We've understood fundamentally why this doodling fact is true. Okay, that means we've gained something. So if we're going to do a doodle 1,000,000 times, let's say this is a million doodles in a row around a shape, we can save ourselves some time by doing 1 single doodle of size 1,000,000, because we know that n1 of n of 1 is n of 2, n of 1 of n of 2 is n of 3, and so forth. So now the question is R gets really big, I imagine we'll use limit notation, does a doodle of size R get more circular? And you may still complain because I don't know what more circular means. And that's kind of reasonable. But the point I want to make is, even though the question is ill-defined, this is still science, because this is how science works. You don't know exactly how to say things precisely or what exactly is going on until you figure them out. And the second thing I want to say is that the statement that we're trying to prove is still kind of vague, but it's shorter. And this is maybe a mathematical statement, which is anytime your statement becomes shorter, you are closer to the truth. So we should feel this warm feeling in our stomachs that we're getting closer and closer to understanding what's going on. Okay, so now I want to explain why it gets more and more circular. And the key idea, I want to be sure that you understand as much as I can manage, because we're going to use it later on. And it's a very basic idea to wrap your head around. And this idea is this, which is if you have a shape A contained in another shape B, then if you were to doodle around shape A doodle of size R, it's going to be contained inside a doodle around B. Let me say that in other words, anything close to a point of A is certainly close to a point of B, because everything in A is a point of B. So if you understand that, I'd like you to let me know by maybe nodding your head or giving me a thumbs up. Thumbs up is probably better. So thumbs up if you basically are willing to buy or understand the following statement, which is if A is contained in B, then the points near A are also near B. In other words, the doodle around A is contained in the doodle around B. So if you kind of believe, if you can buy that, good. I see lots of thumbs up, either physical or virtual. And I'll say it one last time, but I won't just one shape is in another. Doodle around the first is inside the doodle around another. Okay, so now I'm ready to tell you why I'm afraid I'm going to lose my screen share when I do this. Oh, is there a question maybe, or maybe not? I don't know.
I have a doubt whether capital X may be topological for that theorem to.
Sorry, can you say that again? I missed part of the words you said.
Can capital X be topological?
Again, capital X. So all it is a subset. So it has topological, any subset can have interesting, it can have holes, it can have interesting topology. But nowhere in that argument did we use anything about the, I mean, we didn't say anything about, A could be 5 points. A could be a fractal. But that argument was so robust that it didn't care about how crazy A was. As long as A is a subset of B, the points, the doodle around A is going to be contained in the doodle around B. Okay, so granted that, I now want to explain why things get more and more circular. So you start off with some X, which is crazy. I'm drawing it as a very reasonable thing, but it could be a letter with holes in it on the page. It could be anything. And so there's my X. And to start the game off, I'd like to pick a point of it, which I think of being somehow in the middle of X, but that's really not going to matter. And then I want to consider circles around P. And in particular, I want to pick a circle around P that's of radius capital R. And I want it to contain X. So now it means I've got my point is inside X, and X is in a circle. And now I'd like to start doodling. So I want to doodle around my point P, and I'll doodle around X, and I'll doodle around my big circle. And what at least many of you agreed to is that means that the doodle around P is contained in the doodle around X, contained in the doodle around the circle. And then what shape is a doodle around a point? Well, it's a circle of radius R, little r. What's a doodle around a circle? It's a bigger circle of radius little r plus big R. So what we were saying, let me just erase some things here, is that our doodle we're interested in, our doodle around X is contained in a circle of size capital R plus little r, and it's also contains a circle of size little r. And so that in my picture looks maybe really believable because little r is little, as the size might suggest. But now let's make little r really big, and let me draw the picture. So if capital R is size 1 around X, now we'll do a really big doodle of size 1,000,000. Then let me draw my picture. Here's C sub R is going to be a circle of radius 1,000,000. And C of capital R plus little r is going to be a circle of radius 1,000,001. And of course, this is not to scale. And yeah, so I really should, maybe I'll try to draw that better. So it's so when I draw it, it's going to be so close. I can zoom in. It's really, really close. But now the doodle I care about, the border of it is wedged in between these two circles whose radii are off by 0.0001%. So what that means is the doodle is wedged between two circles whose radii tends to 1. Or to say it maybe in a fancy, I do make it formal if you want, you could say the ratio of the smallest, the ratio of the smallest of the small circle containing it to the biggest circle in it goes to 1. Formalize it any way you want. But without a doubt, if when you draw it, it's wedged between a circle, once you take a step back and look at it, between a circle of radius 1,000,000 and a circle of 1,000,001, there's no doubt that it's getting more and more circular. So I want to now declare victory. And so I've now explained the thing we wondered about, and so why it's getting more and more circular. And you might complain, I think you should potentially want to complain, that I only told you what more and more circular meant after finishing the proof. And that seems like it's cheating, right? So it's you just no fair. You should have said what you meant before you actually you moved the goalposts. But the answer, but really this is how science is done. You see something, you're trying to make precise, something seems to be true, and you make it make sense. Maybe as a good example that I think about, hundreds of years ago, you'd have the notion of weight. And then at some point, Newton said that really there's this notion of weight and there's a notion of mass, and they are not the same thing. There's a reason why we think of them as the same, but it's important nature is telling us how to define things correctly. And as we have some vague idea, but then nature will tell us how to really do it. And that's what happened here. Nature said, this is the right definition of more and more circular. And you could say, well, wait, what about another definition? I have another definition. My answer to you is, great. I bet your definition will also work, and you have your own theorem to prove, which is very likely going to be true. And I'm not saying that my theorem is better than yours. I bet yours is going to be really interesting too. Maybe you have something about curvature. There are many other things you could do. There are other definitions, and they lead to other theorems as well. So anyway, that was like fairly hard. That was serious and something you can answer only once you have some formalism. But now I want to tell you another related question that requires something less. So this is something that I heard probably around age 10, not in this language of convex polygons, it was about maybe a square or a pentagon. I'll ask it in a second. So just to make sure we're on the same page, a convex polygon means a polygon with no dents in it. And a non-convex polygon is going to have a dent, like that. So that's my definition by example. And so I'm ready for the question. So let me take this works good. That's a pentagon, obviously. It's not a regular pentagon because you saw me do it in real time. And I don't know what the lengths are exactly or the angles or anything like that. But if you take your ruler out, you'll check that the perimeter of this pentagon is exactly P, or P of X. My pentagon is called X. And so if I doodle around it of size R, here comes the question that in the phrase that I would have heard it back then. If I doodle around it, what is the length of that doodle? How long is that perimeter? And this is a very unfair question because I haven't told you what the individual side lengths are or the angles or anything like that. Yet I'm going to ask it anyway. And the cool thing about the question, of course, is that it doesn't depend on anything but the original perimeter. And now I'm ready to, although I don't know whether you believe that or not, and now I'm ready to ask for if anyone has any ideas. And I don't want a proof. Well, I do want a proof, but all I want is a good idea. What do you think the answer is? What might the answer be? And so if someone can, I'll let the host pick someone to volunteer an answer. And I really, even before people answer, I don't mind if the answer is wrong because there's nothing wrong with a wrong answer so long as you're willing to edit it and it can take you one step closer to the truth.
So there are a couple of answers, P plus 2 pi r square.
P plus 2 pi r squared?
Yeah.
Great.
And
So
there's one answer P plus 2 pi r and an answer pi r square, nr plus P, P plus 2 pi r, etc. Yeah.
Great. Okay, good. So we have a bunch of answers and great. So I like these answers. They can't all be right, but that's okay. They all have some similar flavor. And so they all come from some insight. When you see that, when you see these answers, you don't just want to know where they're right and wrong. You want to know where they came from. And now you could also say this is now an empirical question. So you could actually try it in some examples. And when you do it, you'll realize that in fact, the middle answer is the one you should believe. And so now I like someone who said the middle answer to say what was going through their head. I don't mean prove it. Although if you feel like it, you can. Why did you say, why was it just a lucky guess? You just put symbols. You decide to say some random letters, some in Greek.
Ritam, you're the first one who answered P plus 2 pi r. Could you unmute?
Okay, so when you expand from P of X to X to NR of X, the sides get translated by R units in the orthogonal direction, and the corners become circular, and the total angle subtended by the circular arcs is 2 pi, and the radius of the circles is r. So that's how I'm getting pi plus 2 pi p plus 2 pi r.
Excellent. Okay, fantastic. So what Ritam said was what I was trying to draw in real time, which, well, one thing I did not appreciate is he was insulting my drawing, but I'll let that go. What he said is that the way I sketched it was not so correct. And really what happens when you doodle is around this polygon, the sides end up parallel transporting like that. and these are rectangles. And so already you can see in the new shape, the original perimeter still lives on in this way. And there's your P, which I'm guessing had something to do with that P, and I'm already beginning to have an idea about that. And then you have these things which are circular arcs. Then you realize these are circular arcs. And then, but I don't know what these angles are. But he didn't say why, but I can guess his reason, although they're actually different possible reasons, that these angles all add up to 2 pi, to 360 degrees. And one reason is that you can imagine sliding them together like pieces of pie, I guess, with no pun intended, like that, and you get a circle. And so that's your 2 pi r is the circumference of the circle. Yeah. And so this so the great thing about this is that there are so many things to notice here. Actually, I should have said, even in the past circle argument, where about why things get more and more circular, I should have said that if you know things like the squeeze principle and how limits work, all these things, if you squint, you see in this thing, and here also you see things in geometry problems when someone draws extra lines, suddenly things become transparent. And that's what Ritam did in this case, which is these extra things make it really transparent as to what's going on. And let me say even more, a different way you might have worked out what these angles are is you might have used the exterior angle formula where you, I don't know what you call it, where the sum of where you work out the sum of the angles in an n-gon, like in a pentagon. And you could have done that and you've got the same thing. What I said had nothing to do with that, did not use that, which means that we have accidentally proved that as well. And of course, answering this question, this thing that you might have been wondering in grade school, also becomes transparent too, just by asking about this doodle. And the last bonus fact from what his argument said was that once you understand something, you often understand, you get further questions or further benefits. And here's a further benefit, which I could have asked instead, what's the area of the doodle? And I guess I need to tell you what the area of the original pentagon was. The area of the original pentagon, if you carefully measure it, is A. And so you get the area of the shape is A plus PR, these are the pentagons, plus pi r squared. So that's a bonus fact you get. And maybe for those, if you look at these formulas and you see lots of letters, but really X is a shape. So this is a number, pi is a number, and really these are polynomials in R. And the derivative of the area is the perimeter. That cannot be a coincidence. So that's a question. Why is that true? But I would instead notice something else, which is that this is a polynomial of degree 2. And the coefficients of this polynomial all mean something in geometry. Area, perimeter, pi. They're important things. Okay, so let's generalize. And let's suppose something is convex but not a polygon. So there's something which is like an egg shape, vaguely elliptical. And so maybe to make my life easier, I'm going to prefer to change my definition of my doodle, where I'm going to walk around my shape counterclockwise. And I'm going to stick out my right arm. I have to stick it out so you can see it in the screen. And at 90 degrees and mark in green a shape. And my arm has length exactly r, as people have often told me. And that's my definition, my new definition of a doodle. And I'll leave it to those who know enough or are curious enough to wonder whether I'm doing why is this the same, and why am I doing this? But let me just do this anyway. And an amazing fact, which you can take at least empirically, is that the Ritam's argument does not work at all. There's no polygon, but the perimeter is still has the same formula. The area has the same formula, and this is amazingly true. And so, given that his argument is completely bogus, how could something so wrong feel so right in this case? And so, how do you prove it? And I suspect that you'll have one sort of answer, and I'll give you a different answer. If you want to rigorously prove it, you might use Green's theorem, learn Green's theorem, and give this proof with calculus. Or I'm guessing you likely would say, well, Ritam is okay. Obviously, he's an idiot because his argument doesn't apply at all. But you can try to make him make sense, and try to figure out what you mean by saying you could approximate it by polygons and blah blah blah. And if you try to make him make sense, take his argument and make it make sense, you are following in the steps of Newton and Leibniz. or in fact, people long before Newton and Leibniz in developing the calculus. And both of those arguments are really useful, trying to make precise this big, and you can make precise his argument, or use machinery built up since. Anyway, we were just doodling around things like egg-shaped things, and we've now developed the calculus. Okay, here's another question I saw. This one, maybe also when I was about age 10. I suspect many of you have seen it. So here's here's a question. So I'm going to wrap string tightly around the equator of the Earth, and then instead cut it and then add 1 meter of string and levitate it, tie it together and levitate it above the Earth, so it looks kind of like the rings around Saturn. And so levitate it so it's at a constant height. And my question is, how high off the ground is it levitated? So that's going to be we'll have a poll shortly. So I've had 1 meter of string, and I'm going to ask whether it's maybe I need to say, I won't ask for an exact number, but is it closer to a millimeter or a micrometer or a nanometer? And unlike my previous poll of all the answers can't be right, and most of the answers could be close to the right number. So, but if you don't vote, you are definitely wrong. So there's no harm in voting. At worst you'll be wrong, but you might be right. You have a 1 in 3 or maybe better chance. And you may want reasonably. So maybe I should say, if you're a pure mathematician, you may not know this, but the Earth is not a perfect sphere, but we'll pretend it is. Also, no, I think that's probably going to be enough for now. Great, good. So great. So now hopefully you have a guess. Now my question is, try to have by now you should have a guess in your own mind. Don't do what everyone else says. Don't start watching the results and voting with them. Do you think it's going to be, because there's no shame in getting the wrong answer. The real shame will be in not voting. So what do you think? Closer to a millimeter? Oh, you also, I should say, you may say this is not a fair question because I haven't told you how big the Earth is. But this is you live here, most of you. So you should have some, roughly how big the Earth is. If you need, it's really a shame if you are confused about the size of the Earth. Okay, great. So
I'm starting the poll for the 30 seconds mark.
Good.
The poll's
Don't
in
look at
progress.
it, just vote.
Okay, so it's stabilized almost at a third each.
Okay, that is
31, 35, 35.
That's really amazing. That is close to it. That is a third each. That's that's almost like it was. I don't know whether the election was rigged or something like that. That's I should say that's exactly my feeling. That like it's that I think it's an extremely reasonable answer. That's a third. It's a third. And now, of course, you can actually calculate this when you're age 10. You don't. You'll just use the circle. You'll use radii circle. It turns out that it's in fact way bigger than a millimeter. It's about, this is not the scale because you're looking at it on the screen, but it's about this. It's about this big. I don't know if that's a question from or not. Feel free to ask questions during, I should say. And so here's why. So the reason why is and I should, I think the third is, this is why this is, the reason this is good is because it's counterintuitive. It's good that it was a third, because it makes the question interesting. So here's a cross section of the Earth. And I don't know, again, I don't know exactly the radius of the Earth. Let me call it R. And then I raise the string above it. And now I've added little r string, where little r is 1 meter. And how much more string, sorry, that's the height, the answer. That's wrong. The height is what we're trying to find. But how much string do we add? With the amount of string we added is the doodle around the Earth of size r minus the doodle around the Earth of size 0, the actual And that's going to be 2 pi r. From the formula we had before, it tells us this is 2 pi r, and this is 1 meter. So r is 1 over 2 pi meters exactly. And so it's about 1 over 6. So it is closer to this. And I hope I hope even if you voted for a millimeter, that you still find this amazing the first time you see it. But now, as always, so that's something you can answer as soon as you know about radioactive circles. You don't need to do this entire doodling argument and take limits. But you get more things, such as if the Earth, all you need about the Earth is that it's convex, or that when you tie string around the Earth, you get a convex shape. So in fact, for any shape around any asteroid, this is still true. Around Mars, this is true. No matter how crazy the shape is, the string around the blank puzzle still works. And that's even more surprising than the Earth. Okay, let's generalize some more. Let me give up convexity now. So I'm going to allow dents. And so here's a doodle around the shape with the big dent. And so I can now ask my computer program or empirically work out what's the length of the doodle. And the length of the doodle, the same formula holds for length. For the length, because it's obvious what I mean by length, I guess, which is the length of this red thing. How about the area? Well, the area, okay, what do I mean by area? I think the reasonable thing is not including the whole, and you include everything else. But if you do that reasonable thing, you get the wrong answer. The area is not satisfied the same formula, or I should say the formula is not right. So what do? You realize at some point that, in fact, if you change the notion of area, because clearly you want to double count the area in the overlap. So in other words, if you do that, it turns out the formula still holds. So what did you do? So what turns out is the formula is not wrong. Our definition of area was wrong. We were forced to discover the notion of area with multiplicity. We are listening to nature that's telling us that our definition of area needs to change. And so now comes an interesting question. Let me now do the figure 8. So how do I get the doodle around the figure 8? Now, remember my definition, I'm going to walk around it with my right hand extended, and I will doodle like that. And now I could say, how long is that red line? What's the perimeter of the doodle? And empirically, it turns out that the perimeter does not change. So that's interesting because we're getting a different answer. And so we have a why, or what's happening. And then if you try to work out the area, well, okay, I'm going to tell you the answer, and you've got to tell me the question. The area of the figure 8 of the doodle is the original area plus the perimeter of times r. And now, what do I mean by area? Well, what I do not mean, when I see the area of the figure 8, I would initially guess that's the area of the figure 8. But that's not right. That does not give me the right formula. Nature tells me that's the wrong definition. So now I want us to learn how to listen to nature and figure out what the area of the figure 8 is. And now I'm going to ask you the question. If someone has an answer, a guess, and there's nothing wrong with a wrong guess, tell me your guess, and I'll tell you whether it's right or wrong, or whether it's too high or too low, and you can edit the guess. What is the area of that figure 8? That makes this formula true. And I'll let the hosts pick someone to, since I see hands up, and I think there are probably good ideas there. Okay, so I'll let who should be.
There's one answer saying directed areas and one saying difference between the two lobes.
Can I answer?
Yep, yes, please, whoever said that.
I think our new concept of area should be different for both loops. I mean, on the upper loop, the area between the purple loop and our doodle is the area, and on our lower loop, the area between our doodle and the purple loop is the area. Yeah.
Good. So there's a minus sign. Great. So this answer, several of the answers are going to be logically equivalent. So it's interesting how they're phrased differently. The difference area is this minus that. I hope I have the. And then someone else said difference of the two lobes, which means the area of the big grid should be not this, but plus this and negative that. And another one said, yep, yes, please.
We can think this of a string and unwind the string and then take the area.
Great. And then if we unwound it, you have to figure out how to unwind it. And then things
eventually, can we think it as of a winding number, where if the winding number is not zero, eventually then certain r times will come. I mean, if the winding number is eventually n, then n 2 pi r will be added to the perimeter of px.
So let me extract from, yeah, absolutely. And now let me repeat what people have said, because the insights said by different people are different insights that are really useful. So one of the answers was when you, a couple of these are going to be logically the same, but come from different points of view. One is when you evolve, once you begin drawing, and imagine that you're growing it, you get this with a +1 and this with a -1. This will relate to why the perimeter is the derivative of the area, as it is here too. Someone else said take the plus for the top and negative for the bottom. Someone else gave a reason for a plus, said the reason has to do with the winding, the fact that you're going clockwise or counterclockwise. And so all of these answers are everyone, I think everything people are saying is correct, but even more important than being correct in the short run is that they are like a step towards something correct that is empirically testable. And even though they are correct, they give different insights the way they said it. And so now we have a great way to test this. Oh, maybe to really firmly answer the question, you do, if you say plus this minus this formula holds, that must be the answer. And so here's a different example, which lets us test some of the ideas that people mentioned. And so here, in the previous one, we were forced to consider negative area. Here we have area 2 and area 1, and the formula is still different from the previous cases. Now you have a 2 pi r squared, not pi, and a 4 pi r, maybe not surprisingly, in the perimeter. And so we have a rule to know what the multiplicities are. I'll put question marks here. And we have rules for what this number is. And indeed, as I've forgotten who said this precisely, but it's the what number goes inside here. It's the number of times the path winds around it in a counterclockwise direction. And then that works for everything, and it works for the number 8. So if you don't know what the winding number is, it doesn't matter. If you do, I want to emphasize that this is a notion also from physics. You could test this by running current through this wire. And this is really the same. You should think of this as the same. It is the same. And furthermore, how do you know what this number is? It's also maybe a winding number if you figure out. It's the net number of turns you make as you go through the path. Okay, so now let me go one more to generalize one more step, which is if you have many different holes, many pieces. And so this I think is a picture of some islands, and one of the islands. Let's see if I can make some. There's the ocean, a lake, and that lake has an island in it, and this is all. There's like a big ocean, and now our doodles are going to be like ripples of water. And once you work out what the area is of the doodle, then it turns out that it's again the original area of the islands, the perimeter of the islands. If you'd like, imagine walking around the coast of the island, and you're always walking with the water on your left, and including when you're walking. Oops, that's not even right. And then you have some mystery integer, which you can work out in terms of winding numbers. But what you get is some mystery integer, which is also what's called the Euler characteristic of the islands, which is the number of pieces minus the number of holes. It's a notion from topology, something that gets defined often in a first graduate course. And so by doodling around this map and wondering, asking question, we are forced to have discovered notions of winding number, negative area, Euler characteristic from topology. It just, there's no, somehow it's inevitable that these notions are forced upon us. And then you can ask these questions and even more and generalize further. So you could ask what happens in 3 dimensions. And I feel like that's the first question I would have asked. But then later, when you realize the right question is, well, of course, someone at some point was going to ask about n dimensions. But the question you should try to figure out first is to generalize downward and figure out how to do it in 1 dimension. And I encourage you to do it because it's confusing. Some it's more confusing in 1 dimension than 2. So I'll leave that for you. And let's think about 3 dimensions. And when you wonder about it, well, you need to say what you mean by doodling in 3 dimensions. And so the way I will think about it is you take your 3-dimensional shape, and by doodle, I'm going to go back to my original definition of all the points within R of your shape. And so I picture it like you have your shape, you have this cloud of dust of radius little r, or maybe like or clay, like a layer of clay of thickness exactly all around the entire thing. And so, okay, so now what are the questions you want to ask? We already know the question should be things like area and perimeter. So I'll ask the question about the volume of the doodle. And if you're exploring, you should try to do some examples. So let's start with the example of a box. So we take, I guess I should have had a non-cubical box handy. Here we go, this will work. This is almost cubical, but not quite. So here's a box. And I would imagine a dust cloud or clay around it of thickness exactly r. And my question is, what's the volume of the clay, of everything, of the doodle around this box? And now to save time, let me answer because Ritam already explained what to do in 2 dimensions. So I'll say the same thing in 3 dimensions. So I've got the clay around this box. And okay, the box has height. See, that's H, L, and W if you measure carefully. And what's the volume of the thing around the box? Well, there's the contents of the box, the original volume. There's also a layer of clay around on each face of thickness R times this face, R times this face. So it's R times the surface area. And then also, I remember every time said that around each of the corners, there was a little bit of a circle. So here we're going to have an octant of a sphere, and they'll all fit together. So the volume of the doodle is going to be this. Great. So there's our, and now we can try to generalize. Any questions about that? That's okay. Everyone seems happy with that.
So should we also add the cylindrical volume around the edges? You just added the corners.
Nicely done. Yes, thank you. I was wondering whether anyone would take what I was taking as sort of something really. Yes, absolutely. Did I lie? I think I actually did lie. I was hoping to not lie and just admit something, but I know I did lie. I forgot something. There was a gap, which is if you really pay attention to the shape, as Bharat had said, there's a quarter cylinder here around each of the edges. And so really I should stick inside those 4 quarter cylinders around the vertical ones. They fit together to be a cylinder. That's pi r squared h. And also pi r, so of each of the 12 edges, they glue together to give 3 cylinders. So in fact, there's this extra term. And now something interesting happened that I want to point out, subtle and interesting as well as non-subtle and interesting, which is that's the term. That's the weird term. That's the one, if you ask people to do it, the one they will forget most often is that. That's why I chose to omit it. And furthermore, this, you want to have a formula that works for any convex body. And if you're trying to follow Ritam's argument, you might first deal with a polyhedron before getting to something that's shaped more weirdly. And so what should the doodle around this be? You might be able to guess much of it, which is you take the volume, that's okay. You take the surface area times r, you can see the things on each face. And then around each of the vertices, you can see part of a sphere, and they actually all fit together. So we can explain all of these. But you also have these things which are no longer cylinders, right? They're no longer quarter cylinders. And you don't, I guess you try to work out what that angle is. That gets weird. And it's not h plus l. What do you mean height plus length plus width of this? It's unclear what this means. So there should be some, I don't even know what to even say about this. There's a huge mystery about what this means. And so maybe the next thing you'll check is the case of a ball. And if you do this for a ball, you get of radius capital R, you get 4/3 capital R sphere of radius capital R, you get the volume of the sphere plus the surface area times R plus 4/3 pi little r cubed. And then here you get some mysterious thing, 4 pi r times r squared. So the thing that wants to be height plus length plus width of a sphere is 4 pi r. What is that thing? It means something. And if you believe that, maybe I'll ask the same question for different shapes. If you believe that volume is important and surface area is an important geometric notion, and the unit sphere's volume is an important notion, then this extra thing, nature is telling us that there's some important sister of these other three sisters that must be meaningful and is trying to tell us something. Okay, so now let me, now it's 9:30, so I'd like to end with a problem and tell you the answer. Just as I want to tell this to you because this is one of my favorite problems of all times, because it comes out of, and also because this is something I heard about when I was 17, I think. Because it's Olympiad style problem. And I love how, like the best Olympiad problems, it connects to some very deep ideas. And so this rule, this problem, the history, I have had interesting discussions where people from St. Petersburg claim it as their problem, people from Moscow claim it as their problem, and they will argue and fight over it. So the problem is this: you have a train company, which I guess is a train company. I guess the train line goes between Moscow and St. Petersburg. And the rule is that you're not allowed packages whose height plus length plus width is more than 1 meter. And so the question is, can you take a box that's illegal and cheat by fitting it in another box? You can't just fit it in a corner because of the height of the first box is less than the height of the second box and so forth. But maybe you can like squeeze it in some diagonal way and cheat and then bring the illegal box in. So the question is, can you do that? And there are hints of the problem. One is, the most important hint is that if you've done enough mathematics, you know that if you argue mathematics with the Russian is always right. So you cannot cheat. The answer is you cannot cheat. And then the next question is, why is the Russian right? And now I'm going to tell you why in terms of doodling. And it's sort of, I love this because it's sort of a devastatingly fast thing. So suppose you have a box, and one box is another box. Then the dust cloud, the neighborhoods of the first box is that it must be contained in the neighborhood of the second box. This is this thing that many of you gave me a thumbs up 4 ages ago. You've already agreed to it, and you can't take it back. So it's so the doodle, the dust cloud around the smaller box, is contained in the dust cloud around the bigger box. And then we also worked out the volumes of the neighborhoods of the boxes. So for the smaller box, it's volume, area, height plus length plus width, 4/3 pi r cubed. And for the bigger box, we know what that is too. And then being a mathematician, you just can't stop yourself from canceling these out. And now let's do what we did in the very first doodle. You want to make a really big doodle, or doodle and doodle and doodle. So r is going to go to infinity. Maybe if you want, divide by r squared over r squared, and take limits if you want. But basically, if you have two quadratics and one is always bigger than the other, then for sure the leading terms of this guy must be at least as big as this guy. So you must have that this term is at least as big as this term. And again, I can't stop myself from canceling the pi's, and that's it. We're done. Problem solved. So out of nowhere, the answer just got done, and it was really the same. And really, it was the same kind of doodling, just in more dimensions. Okay, great. And so the last thing I'll say, and then I'll be done, is that this connects to lots of actually real current and old mathematics. One of Hilbert had his famous problems from the start of the 20th century, 23 problems to guide the future of the development of mathematics over the century, and to a surprising extent, it was true. And the first question to be solved was the following, which seems very special but connects to some deeper things, which is you take your if you take a cube and a tetrahedron and you cut this up into pieces in nice ways with a nice straight knife. Don't do this with Rubik's cubes, but imagine it. And you rearrange the pieces. Can you rearrange it to make this tetrahedron? And the answer is, well, obviously the volumes are different. You can't. So there's this one invariant. So let's say they have the same volume. Can you do it? And in dimension 2 with polygons, you always can. And that's an interesting, fun problem to figure out. But in dimension 3, it's not so clear. And it turns out that you cannot. And that's because there's something like volume that in 3 dimensions that's not volume, that's some variant of our mystery height plus length plus width invariant, which will distinguish these two things. And so once again, this is a sign of, is the same thing that turned up in that Russian problem in a very different way. That also prevents these two from being the same. Okay, and then so you'd want to do this in dimension n, and the thing you'd hope is that there should be for an n-dimensional, okay, you may want to see an example of something n-dimensional. So here's something which is n-dimensional. It looks two-dimensional because it's on your screen, but it's really four-dimensional in my over here. And so the volume of the doodle is always going to be the original hypervolume plus the hypersurface area. The last thing is going to be the unit hyperspheres volume. And in between, you have more and more and more of these new kinds of these new creatures that are volume-like. And so this is something which has been underlying many ideas of mathematics in geometry, string theory, and so forth, which I can tell you about if you want in the question period, or else I can tell you privately later too. But let me just sort of sum up what I've been talking about, which is we spent all our time talking about one single kind of doodle, and there are similar stories with so many other things, where you just look at you start doing something, you notice something, you ask questions about it. You think, I wonder if this is true. You have guesses. You try to see if they're true. You prove them. They lead to new questions. And in the course of doing it, we were forced to discover the triangle inequality. We had calculus, the squeeze principle. We've had things from electricity and magnetism. We had topology, a Hilbert problem. It just goes on and on and on. But somehow that if you look in nature, all these notions are there once you start pulling at that string and just seeing where it leads you. So I guess the lesson I want to get across is that if you look, once you know how to look, that everywhere you look, even behind really trivial looking doodles, you can find mathematics and science of amazing beauty and power. So thank you very much.
Wow, that was a mind-blowing talk. Thank you very much for that. Like starting off with something as simple as what all of us used to do in our childhood from the age of 4, 5, etc., coming to what is currently a research problem in math. That is absolutely remarkable. Thank you very much for this wonderful evening we have had and morning we have had, hopefully. So we now open for a short question answer session. So preferably type it in the chat. I already see a couple of questions in the chat, so I'll read them out first. So is there any fundamental significance of the quantity h plus L plus B for cuboids or 4 pi r for spheres, which you mentioned?
Yes, and I almost don't, maybe I should say, yeah, I can, my one word answer is yes. And the meaning, but the meanings are multiple. And so they're multiple, and of course they're yet all the same. Maybe I won't even say what it is, but let me give you, great, I will even tell you how to define it in general for any dimension. But let me just give you an example of the, that if you take, okay, here's an example from astronomy. And so in the last decades, we've discovered more and more planets and other solar systems. And how the earliest ones were discovered were when you have the sun, star, and if the planet's going around star, and you were so lucky that the plane of its ecliptic is in our direction, then we'll notice the star seemingly getting dimmer a little bit every so often. And that tells us how often this alleged planet's going around the star. And then it also tells us roughly the size of the planet by how much dimmer it is. And what are we getting as a planet is rolling around the sun? We're getting something like the average shadow of the planet. And that's the surface area divided by, the shadow turns out to be the surface area divided by 4 of any convex shape. There's like an interesting fact. When you take a random shadow of a tetrahedron, it's going to be one triangle. That area, even the average shadows will always be the area of a triangle. One of these triangles. Well, why? That's like a cool fact. Is it 1? Am I? Yeah, I think that's right. Good. So similarly, in what is the thing that's like length plus width plus height? You take your object and you take its average shadow on a one-dimensional thing, on the z-axis, say, as you spin it around. That thing is up to some universal constant, that mystery number. And then that means you can define this, the k-dimensional variant in n dimensions, is you take your n-dimensional thing, you take the average shadow on a k-dimensional thing, and that is going to be up to some universal constant, the same thing. And then it's very important as the circumstantial evidence of how important it is was the Hilbert problem, the Russian problem, and actually there are many others as well. So this notion comes up repeatedly, and it's less that there's the answer of, look, whenever you see this, you should expect it, and more that over time your intuition expands to realize what this really means.
Thank you, sir. That was a beautiful answer. And there's one doubt from the Hilbert problem which you mentioned. So is there any condition upon how small the pieces can be in the Hilbert problem? If there isn't any condition, could I just cut it into small enough and change it into one another?
So the one thing is it has to be straight line cuts and a finite number of cuts. So you can't just say that the cardinality of the two sets of points are the same. That's cheating. You can't in real life doing that. No Banach-Tarski nonsense. So right, you have to make your problem precise, and the precision of the problem will be only straight line cuts and only finitely many cuts. And then it's all legitimate.
Thank you. Bijan, could you voice your question? I'm not sure I got it right in the chat.
Sure, thank you. Are the inequalities for the regarding the subset where that inequality of that basically that neighborhood doodling the neighborhood, is that valid for X, A and B be topological spaces? For the neighborhood is defined for topological space, but the proof here used is for circle of radius R, where the distance function is not defined in topological space unless it's metric space.
Exactly. So right, that's a good question. So you need a metric space in order to make sense of this. So as long as otherwise, as you say, there's no meaning of what the neighborhood. You need the notion of size.
But neighborhood is defined. Neighborhood and open sets are defined in topological space. Only the metric isn't.
It's true. But the problem is the language. The word neighborhood is getting overused in that case, where it's really in some sense a bad choice of word for me to use size R neighborhood, but it's just a lack of enough words for these things that I cannot think of I'm not certain, but I mean, to make the question becomes super interesting when you ask, are there cases where there is no metric, obviously, but it's a topological space and there's still a valuable sense in which this notion makes sense. And I could absolutely believe that if you make let me make a different variant of this, which is do something very discrete. Have a bunch of points inside z to the n, the integer z to the n, and you have like a polyhedron, and you do similar sorts of things. There you are in the topological space is lost, but the metric is not quite. You can still make statements there too. So my general answer is going to be that I can make it precise the way I made it precise, and it makes sense. But there are going to be additional places and ways in which you can make it precise. And then so this turns into a question back for you. I think for an absolutely general topological space with no other hypotheses, I have a hard time imagining how to make it make sense. But if somewhere in between the two, like there are topological spaces that emit different metric structures. That's a good example but now you seem to have different notions of Arc neighborhood. But somehow the answer is, maybe I should basically just say, the question is good, but you have to refine it. And when you refine it, you're going to have some very interesting answers.
Thank you, sir. And Professor B.V. Rao had a question. So could you?
No. I only was mentioning that for general metric spaces, it is not true to say n1 of n1 of x is equal to n2 of x.
That is a very good point. And the question for others then is, what maybe I feel like the question for everyone else then is, why did he say that? What did he mean? What are the examples? And what were the things which makes it be true that is not going to be true for very general metrics? Yeah, that's a great, yes, that's a good point. And the best points lead to people to wonder about stuff. So people should think about that and treat it as a question for them.
Thank you, sir. And one more question. So how do we intuitively define volume and areas for non-oriented surfaces?
I feel like the best answer is to say yes. That's a great question. Right. So if you have a Mobius strip, Yeah, right. So I'm not going to answer the question, but I'm going to discuss the question, which is, and restate the question, which is, as an example, on a Mobius strip, I mean, a literal one with a piece of paper, which will now formalize and figure out what axioms we want to include. The notion of area still is kind of there, right? I mean, it's not like there's no notion of area whatsoever. There's a worry about sign, and if you go all the way around, you have a problem with it being consistent. But locally, there's no problem with it being consistent. You know, with the area, you have a little piece of paper, and then locally, everything is kind of orientable. So good. So I think that's the excellent question. Like it makes sense of, right, and answer that question. And in order to do that, you're going to need to put some hypotheses down. And what are the hypotheses to make the question a good one? There can be more than one choice. But maybe as a toy model, literally a toy model, the Mobius strip is a good one. Like how you should be bothered if you're a high school student and you're happy with area, but when you have a Mobius strip and you go all the way around, your answer screwed up. Or you should be bothered if we send a rocket into space and it heads off in a certain direction, and then 50,000 years later it comes back from the other direction, but now the pilot's left-handed and somehow still alive. Like somehow great. So I like that question because topology is both analysis and topology are both inherent in that question.
Thank you, sir. And are there any other questions? Please feel free to write it out in the chat or maybe unmute yourself. We'll wait for a minute or so.
So could you please explain the Euler characteristic via an example?
Sure. The best example, let's see, Euler characteristic is an invariant, and it's without saying what topology is. Let me instead say some of the examples of Euler characteristic. One of which is, you might have heard that if you have a map on well, let me just use letters. V minus E plus F equals 2 is an example of the 2 is an example of Euler characteristic. So you might have heard of V minus E plus F equals 2 in the follow. If you've heard that equation, you know what I'm about to say. Imagine you have you have a map on a surface and you have a bunch of countries and with borders. And now I need to start to add hypotheses that I later want to remove. But let's say all the countries are, you don't have any disconnected countries, no islands. It's all landlocked. There are no oceans. And all the countries, there are no little countries contained in other countries. Every country is like one piece. There isn't another piece. And then you could count the number of vertices where more than one country meets. Maybe there's a place where 4 countries meet. You can count the number of edges between 2 countries. Maybe we also need to really make sure that any 2 countries always meet only in one edge. And it turns out the number of vertices minus the number of edges plus the number of countries is always 2. I guess we need 1 country around the border, 1 or 2, depending on how you do it. And so why is that invariant? If you did the same thing on a very strange planet that was shaped like a donut, like a torus, you wouldn't get 2, you'd get 0. Or if you did it on a kind of planet that had 2 holes in it, well, you get something different. I'm not going to even get into what you might do if you had countries on a Mobius strip or on a Klein bottle, but that becomes an interesting question too. And then another question is, why do the countries have to have no holes? What happens when you have holes? What happens if they have several pieces? And then the question gets more and more complicated. But now I'm simply going to say the following thing. Now I'll actually define Euler characteristic. You have an Euler characteristic is you take your shape and you cut it up into pieces where you have things that look, I can't use the word topologically without defining it, but they're like countries. They have no holes. They're just like shaped basically like spheres, just deformed. And then the borders are all are shaped like spheres, just deformed. And then the borders of the borders, maybe I'll stick to 3 dimensions. So you have this huge, complicated shape, solid shape, and you cut it up into things that look like spheres, and their borders are all things that look like circles. And then you have edges and vertices. So you have vertices minus edges plus the number of 2-dimensional things minus the number of 3-dimensional things. That's the invariant. And that's true no matter how you cut the thing up into pieces. That's the Euler characteristic. It's not a great definition, not perfect, but it leads to the big question of why is that well defined. Actually, maybe one last thing I'll say related to that, which doesn't sound like it's the same thing at all, which is if I put n cups in a row, I someone apologize because I don't know what people know and don't know, but this is great no matter what you know anyway, which is you have n cups in a row numbered 1 through n, and I reach in with my 2 hands and I swap a pair and I swap another pair and I swap another pair, and I keep doing this and I do it 2021 times. And the answer is at the end, they cannot be back in the position in which they started. And so that is, the question is, why is that true? And maybe what does that have to do with Euler characteristic or Mobius strips or anything like that? Those are all later questions. But that the question, as I asked it, is something someone in high school could do, not easily, but without knowing anything fancy. And that's an example of something like an Euler characteristic, but it's valued in Z mod 2 for those, Z mod 2 for those who are happy with that notion.
Thank you, sir. Thank you.
Thank you. That was absolutely a lovely explanation, I must say. Thank you very much for that once again. So I think we can now come to an official close of the session. So once again, please join, all of you, please join me in thanking Professor Ravi Vakil for this wonderfully prepared session he has given and captured everyone's attention right from grade 8 to undergrads all the way to professors also in various institutes. So really, thank you very much for that. So as you can see in the chats, you're getting plenty of appreciation here. So thanks for that. So finally, so this concludes the STEMS 2021 qualifier camp. So thank you. Firstly, congratulations to all the students who have managed to clear the examination, and thank you for attending these lectures, and huge thanks to all the professors who have agreed to take time to talk to these brilliant young minds. So thank you very much for that. And never to forget, a special thanks to Amik for helping coordinate everything so smoothly. So thank you very much. And
thank you, Aniruddhan, and thank you, Professor Ravi Vakil, for this beautiful concluding session. It was really, really amazing. Like from the title of your talk, it was really wonderful. I was wondering that how can you, and it was like really satisfactory. It was really good. Thank you.
Thanks for inviting me to join.
So it was our pleasure to have you on our show. It was really wonderful.
Okay, so I think this should be the final conclusion from STEM's 21's qualifier camp. So hope to see you all soon, and stay safe. Thank you. Goodbye.